Hi, welcome to this lesson on number patterns, geometric sequences. Solving a geometric sequence problem, question 2. Consider this following sequence: 128, 64, 32, all the way down to 1/8. How many terms are in the sequence and which term will give you a value of 4? So there's two parts to this question. How many terms are in the sequence and which term, so the position in the term, will give you a value of 4. So will it be the second term? Probably not. The second term is 64. It's definitely not the third term or the first term. It's definitely not the last term. So maybe it's the fourth term, the fifth term, the eighth term. Well, we're going to figure that out. All right. So first of all, let's check if this is a geometric sequence, which can be written as a times r to the power n minus 1, where n is a natural number. Well, firstly, if I take t2 divided by t1, that's 64 over 128, that gives me a half. So that's my r. But let's check. What about 32 divided by 64? That's t3 divided by t2. That's also a half. So we can suspect here that the constant ratio r is a half, and the first term is given as 128. So let's rewrite that. T sub n is equal to 128 times a half raised to the power n minus 1, where n is a natural number. So that is the general term of this geometric sequence. However, we want to know how many terms are in the sequence. So if I listed them out like I have there, 128, 64, 32. Now, we know that the constant ratio is a half. So if we multiply by half, we can probably see that the next term is going to be 16. So let's keep multiplying by half and see if we can write out the full list until we get to 1/8. So 16 times a half, that's 8. 8 times a half, that's 4. 4 times a half is 2. 2 times a half is 1. 1 times a half is a half. A half times a half is a quarter. And a quarter times a half is an eighth. So I can actually count the number of terms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 terms. So I would say n equals 11 terms. But that was quite tedious and long to do. And sometimes you might get problems that end up being 50 terms long. Now you don't want to keep multiplying by the ratio to see how many terms there are. So we can do a bit of algebra here to help ease our lives. So we know that the last term, which is t sub n, we don't know what that n is, that is 1/8. But we know that that's got to equal to 128 times a half raised to the some power n, that's what we're looking for right now. That'll be the last term, minus 1. So here we are solving an exponential equation. So I get rid of this 128 first by dividing, or essentially multiplying by 1 over 128 on both sides. And that'll leave me with a half raised to the power n minus 1. So to get rid of that 128, I divided by 128 on both sides. But doing this product, you can check that you get 1 over 1024 equals a half to the power n minus 1. But 1024 is a very special number. When we work with exponential equations, we try as much as we can to get the bases matching. Otherwise, we'll have to introduce logarithms to solve for the exponents. But 1024 can be written as a power of 2, that is 2 to the power 10. And that is the same as 1 over, or half, raised to the power n minus 1. Now, my exponential laws will allow me to write this term here as 1 over 2, all raised to the power 10. The reason being is that if I use my exponential laws, I get 1 to the power 10, which is just 1, and then I get 2 to the power 10 in the denominator. So I get this exact same term back. So that is why knowing your exponential laws is critical. So let's clean that up a bit there. So we have 1 over 2 raised to the power 10 equals 1 over 2 raised to the power n minus 1. Now the bases are the same. So I can equate the exponents. 10 equals n minus 1. But if I add 1 to both sides, I get 11 equals n. And that is exactly what we verified when we expanded out the sequence manually. So therefore, you have a total of 11 terms in this geometric sequence. Next, you're going to find out which of those ones give you a value of 4. Well, if you look quite easily here in the sequence list here, that's the first term, second term, third term, fourth term, fifth term, sixth term. So T6 will equal 4. And that'll give you the position, which is the sixth term. So which term will give you a value of 4? The sixth term. Right, you can also solve it algebraically like we did here. You could solve the equation 4 equals 128 times a half to the n minus 1. So let's give that a try. Let's see how far we get with that one there. So I'm just going to clear this for now. There we go. So T sub n, as we recall, was 128 times a half to the power n minus 1, where n is a natural number. And we want to find which n value here gives you a value of 4. So 4 equals 128 times a half to the n minus 1. Divide both sides by 128, so you get 4 over 128 equals a half to the n minus 1. But 4 divided by 128, that can be simplified down to 1 over 32 equals a half to the n minus 1. 1 over 32 again can be rewritten as 1 over 2 to the power 5, because 2 to the power 5 is 32. And then I use my exponential laws again, and I can rewrite that as a half to the power 5 equals a half to the power n minus 1. Therefore, since the bases are the same, I can equate the exponents. 5 equals n minus 1. And therefore, adding 1 to both sides, I get n equals 6, which we did verify when we expanded out that sequence. Okay, so knowing how to do it algebraically is very important because sometimes you won't be able to list out the sequence very nicely, as it could be the 20th term, the 30th term, the 100th term. So being able to solve the exponential equation is important. All right, I'll see you in the next one.